When Davisson and Germer were conducting this experiment that eventually proves the wave properties of particle, they actually found the correlation between the accelerating voltage that they applied here and also the angle in which they find the diffraction peak to occur. So this voltage over here, we are going to call it as the accelerating voltage, because this voltage has the purpose of accelerating the electrons that pass through it. Okay, so if we increase the voltage over here by shifting it to the rheostat to the right hand side, we are covering a greater potential difference. So we are setting up a greater potential difference between the two electrodes. So when you are setting up a greater potential difference across this pair of electrodes, essentially you are accelerating, you are creating a stronger acceleration for the electron that pass through it. A greater potential difference will cause a greater acceleration to the electrons that causes the final speed of the electrons coming out from the device over here to be faster. So by having a faster electrons coming out from this device, you're actually changing the matter wavelength of the electrons itself. We talk about electrons behaving as wave, right? So if the electron is moving faster, you're actually changing the wavelength of the electron, or the electron wave. You're changing its wavelength in a certain way. You are making the wavelength shorter, or making the wavelength longer. Later we will see. But by changing the wavelength, we are actually manipulating the result of our diffraction, causing the peak in which we find the diffraction peak. The angle will be shifting. Okay, the change in the wavelength of the electron wave causes the diffraction peak to shift in angle. So in this particular video, we are going to prove mathematically how does changing this accelerating voltage here eventually result in the shift of this angle over here. But to understand the whole setup better, probably we need to talk about a little bit more about diffraction maybe. Okay, so it is found that the angle in which maxima are detected varies according to accelerating voltage. Just as I said earlier, if you increase the accelerating voltage, you might change the angle in which you find the diffraction peak to be at a certain other angle. Okay, so these two are correlated with each other and we need to know why. Okay, so let's try to understand the diffraction. Where is the diffraction? Why is there a diffraction? We have to understand it more clearly. Okay, so why does the angle in which the maxima are detected varies according to the accelerating voltage? Why are they related to each other? We need to understand the diffraction first. Okay, we know that the pattern form is a diffraction pattern. Okay, it's diffraction, only you can find that kind of peak, right? So, but this diffraction, you have to be very clear that it formed because of two factors. The first factor is because electron behaving as wave. If your electrons are behaving as wave, only you are able to produce a diffraction. If you are able to produce diffraction, only you are able to see this kind of peak. Okay, that's grammar problem. No, it's okay. Okay, the second thing that I want to talk about that causes the diffraction pattern is because the crystalline lattice of nickel crystal. We previously said that before we heat up the crystal, right, it was a polycrystalline structure. But after we heat up, right, we create a wide area of uniform nickel crystal, and that uniform nickel crystal causes us to be able to produce that kind of diffraction pattern. So you know that the crystalline lattice matters and also electrons behaving as a wave. These two are the main reason why I'm able to observe this diffraction pattern. So now let's try to understand why. Okay, so because we imagine that electrons, not imagine, yes, it is indeed true that electron is going to behave as wave. So we are not going to illustrate the situation as electron particles approaching this nickel crystal. Instead, we are going to draw them as a wave. So each wave over here will be representing one electron wave. So one electron is equivalent to one electron wave. So this is one electron, this is another electron coming towards your nickel surface over here. So because you heat up the nickel crystal already, it forms a very uniform kind of crystalline lattice, right? So you can expect that the distance between all atoms, all nickel atoms, the distance between them will be the same. So distance over here and the distance over here and the distance over here will be the same. Okay, so when you have your electron wave incidenting onto the nickel crystal, what happens is it will get reflected off, or in the more proper word, it will get scattered off, it will get deflected to a certain direction. Okay, so let's say today if you are deflecting in many different directions, but let's say if you deflect in this particular angle, which is 50 degree, it is found that the reflection or the deflection or the scattered electron here, the difference in path traveled by this first path and the second path here, the difference in path, or R2 minus R1 here, this path difference here, is actually if it's equal to m lambda, then according to our learning of constructive and destructive interference, if this path difference equals m lambda, then the electron wave, first electron wave and the second electron wave that scattered off the nickel crystal will actually constructively interfere, and that will result in a strong electron wave being reflected off in this particular angle. Okay, so the idea is similar. It applies a little bit of what we learned from thin film, in which wave will get reflected off. That is what we apply from thin film. But we also apply something that we learned from diffraction grating. So we can think of all particles here to be one source, another source, another source, another source. So there are plenty of sources of electron wave. So this particle here will will reflect its own electron wave. This nickel crystal here, this nickel atom here will emit its own electron wave. This nickel crystal also its own electron wave. This nickel crystal also its own electron wave. But at an angle of 50 degree, we can find that the path difference for all these electron wave, they are all differ by m lambda. So if their path difference differ by m lambda, they will constructively interfere, resulting in a strong peak to be observed at this angle 50 degree. Okay, so we're applying a bit of thin film idea, in which we're talking about the reflected wave that we are going to observe its interference. We are applying a bit of diffraction grating, because we can think of all these nickel atoms here to be, each of them to be one source, so there are plenty of reflection, that's why they form a diffraction pattern. All these reflected electron wave overlap with each other. There are many nickel atoms, so there are many reflected electron wave, so they are overlapping with each other, forming a diffraction pattern. And that is how the idea of this electron diffraction comes to occur. Okay, so because this is diffraction, similar diffraction grating, they are going to apply a similar equation for diffraction grating, which is d sine theta equals m lambda. Okay, so you can think of these particles here, because they are these atoms here, because they are evenly spaced, we can think of it something like a diffraction grating. Okay, so I know this is a bit complex for you to understand, but I probably need you to just understand it roughly. Okay, because if you want to answer the question for this chapter, it's not that difficult. You don't need to know all this theory, but it's good to roughly know that this kind of experiment is actually somehow related to diffraction grating. So because it's somehow related to diffraction grating, you'll be applying a similar equation to what you have learned from diffraction grating. Okay, so that's the kind of idea I want to portray here. I'm not asking you to understand everything in very detail. You roughly know how it comes to become constructively interfering. Then you know that because it behaves similar to a diffraction grating, then this equation is still valid. Okay, so how do you relate between the accelerating voltage here and the angle over here? There's a long derivation that I'm going to progress through, so you listen carefully. In the meanwhile, you might need to review some of the things that we have learned from previous semester or from previous chapters. Okay, so yeah, just bear along and write with me. Okay, so first of all, where am I supposed to see? Okay, so if we increase the accelerating voltage, means by we are shifting this rheostat to the right, we are introducing a greater potential difference across electrode A and electrode B. So previously it was a small potential difference between A and B, but now it becomes a larger potential difference. Okay, so what's the effect of it? If we increase the accelerating voltage, it will cause the acceleration underwent by the electrons to be greater. You undergo greater acceleration that results in the final kinetic energy of the electrons to be a greater kinetic energy. So it will escape, the electrons will come out from electrode B with a higher speed, a greater speed, or a greater kinetic energy. So if you want to prove it mathematically, this is the way we do it. Okay, it's very long, but bear with me. So work total is equal to change of kinetic energy. This is what you learned from work energy and power from last semester. The total work done on the electron will be equals to the change in kinetic energy experienced by the electron. This is total work done on the electron. This is the change of kinetic energy of the electron. Okay, so if we focus on what happens to the electrons, okay, let's draw an electron over here. What happened to the electron is the electron will be experiencing a force in the opposite direction of the electric field. So this is force electric. Okay, the electron here is experiencing a force in the opposite direction to the electric field. So the electric field is pointing to the left, that's why our electric force is pointing to the right. So this is the only force acting on the electron. So that's why even though we are talking about total work done, because there's only one force only, the total work done is actually the same as the work done by the electric force, because there's no other forces here already. We are not talking about gravity over here. There's no other forces, there's only electric force only. So the total work done is essentially the same as the work done by the electric force. Okay, that's how we progress from the first line to the second line, by saying that work total is equal to the work done by the electric force. Okay, now we are going to go back to chapter 1. Chapter 1, when we learned about work done, when we learned about potential difference, when we learned about electric potential, energy, all those things, we learned that for work done by electric force, okay, I'm going to write it here, work done by electric force is actually equals to negative change of electric potential energy. And if we expand it, we can say that it's equals to negative Q delta V, where this is the charge interacting with the electric field, or the charge moving through the potential difference, and this is the potential difference undergo by the charge that is moving. Okay, so this will be the work done by electric. Of course, you have another counterpart of it, which is work done by external. So work done by external, it will become positive delta U, so it will be Q delta V. Okay, but don't need to worry too much about the second one. We're talking about work done by the electric force. So now we can change this work done by electric force to be equal to negative Q delta V. So delta V is always potential difference, final minus initial. So our final is B, our initial is A, because we're moving from A to B. So this one will be VB minus VA. Okay, of course you can open up your change in kinetic energy to be K final, which is the K at B, and your K initial will be the K at A. Okay, and the charge that is moving through the potential difference is an electron. So we are going to replace this Q here with the Q of an electron. Okay, so this is how it progresses to the fourth line over here. Again, this is not negative bracket, this is just the symbol for electron. This is Q of electron. I'm not saying that Q E minus, this is not minus, this is E negative, representing electron. Okay, so what we are going to assume right now is when the electrons come out from this opening over here, the electron comes out with nearly no speed. Okay, it comes out to be at rest. Then it is the pair of electrode over here that functions to pull it to accelerate to the right. So when it comes out from this filament over here, it's nearly just at rest. So we can think of it as the kinetic energy of the electron at A to be 0. So when it just arrived at A, it arrived with nearly 0 speed, so we can safely change Ka to be equal to 0. We can change the charge of the electron to be negative E, that's the charge of electron, where E is 1.60 times 10 to the power negative 19. E has no negative sign. You have to put in the negative sign in front of it to make it a negative charge. Okay, E is elementary charge, it does not represent electron. So E here is the magnitude of element, or the magnitude of charge of electron and proton. So it's 1.60 times 10 to the negative 19 without the negative. E does not have negative, but because it's electrons charge that we're talking about, we have to add on negative to make it negatively charged. Okay, so VB minus VA, we're going to call it VBA. Okay, some call it VAB, some call it VBA, but you get the idea, it's VB minus VA over here. So because there's a negative in front, negative you cancel out, so you're left with E VBA. So essentially, the kinetic energy of the electron when it arrives at this point, the kinetic energy will be called K, and it's equals to electron, and is equals to elementary charge multiplied by the accelerating voltage. So through this equation, we can know that if we increase our accelerating voltage, if we increase V, we are going to increase K. Okay, so this is how we relate between K and accelerating voltage V. Okay, so now we are going to move on to say that the increase in kinetic energy actually means by the speed of the electron is going to increase when it arrives at point B. Okay, if you have a greater accelerating voltage, the electron that comes out from this pair of electrodes will be faster, so V will definitely increase. Well, it's a simple equation to prove. So you know that if K increase, that means by your speed is increased. your mass is kept constant, it's still the same electron, so the mass is the same, so K increase means V increase. Okay, so I can substitute K to be equals to EVBA over here, bring this equation over, then I can rearrange this equation. Now I can say that the speed of the electron is actually the square root of 2 EV or 2K, because K is equals to EV, right? It's equals to 2K over M, or it's equals to 2 EV over M. So this one will help us to find the relationship between the speed and the accelerating voltage. So we're relating between the speed and the accelerating voltage over here. Okay, we can progress further to say that this increase in speed when it exceeds this electrode here means by the electrons that come out from this electrode, it's going to have a greater momentum, because P is equals to mv. If we have a greater speed, that means we have a greater momentum coming out from the electrode. Okay, so we can again open it up. K is equals to P square over 2m. How do you get K is equals to P square over 2m? You just take this equation, shift the take this equation, substitute mv here to replace it with P. So you make it to become, let me write it down. Okay, instead of talking, let me write it down. I'm going to scribble it here. Okay, so K is equals to half mv square. So what you can do is you can multiply m over m to this equation over here. Okay, it might look weird at the start, but you multiply m over here. M over m is 1, right? So you are not changing the equation, but you are making the equation to be a new format, which is 2m underneath. Then you have 1 m square v square out there. Why do you want m square v square? It's because you can now make it to become mv square over 2m. And this mv here is actually just P. So essentially you change it to become P square over 2m. So K is equals to P square over 2m. So if you rearrange it, P will be equals to square root of 2mk. Just rearrange it. Then K you can substitute with EV over here. Then you get this equation. The momentum is equals to square root of 2mev. Okay, there's no equation that you need to memorize over here. I'm just showing how everything relates to each other. Later on in class, I will do a summary to show how everything relates to each other, and there's no equation that you really need to memorize actually. Right now, the equations, the derivation might seem complicated, but to solve a problem is actually quite direct. Okay, so don't worry too much. You just follow along to understand the concept. The purpose is to understand the concept here. Okay, so this equation here helps us to relate between the momentum here and also the accelerating voltage. So you see the idea is I try to relate everything back to the accelerating voltage. Relate everything back to the accelerating voltage. Okay, so again, if the increase in V, by increasing the accelerating voltage, we are causing the momentum to be increased. Okay, so the increase in V causes increase in P. Okay, next. So if we increase our momentum already by using the equation that we derived in the previous video, which is P lambda is equal to H over P, if we increase our P, if we increase our momentum, it will cause our lambda to decrease. So now for the first time, we can see that the increase in accelerating voltage will cause the electron wavelength to be decreasing. Okay, so of course you can substitute P with square root 2mev over here. Then this is the equation for you to get lambda and relate it to the accelerating voltage. Again, don't worry too much. This is just to understand how everything flows. In class, I'll do a summary to make things unpack it to be easier. Okay, so this is how we relate between the wavelength back to the accelerating voltage. And from here, we can see that we can sort of make a small checkpoint and say that the increase in accelerating voltage actually causes our wavelength to decrease. Okay, so if it causes our wavelength to decrease, it actually will cause the theta to become smaller. Why theta will be smaller? Is because we are not changing D. D is the distance between the nickel atom that we looked at in the diagram earlier. The distance between one nickel atom and the next nickel atom is D. That one is not changing. So if we are reducing our lambda over here by speeding up the electron, we are reducing the lambda. So if you are reducing the lambda, it will cause the right hand side to be a smaller value. So the left hand side need to be equal to the right hand side. So the left hand side will have to be a smaller value as well. So if you're not changing D, how do you make the left hand side smaller? You have to decrease the angle, right? So therefore the angle should be decreasing. Okay, so this equation again is not in syllabus for this particular chapter. For chapter 7, this equation is relevant, but for chapter 8, this equation is not required. Just know it for concept. Okay, so now we can make a conclusion. By increasing the accelerating voltage, it will cause the final speed or final momentum of the electrons to increase. Then this increase in speed or this increase in momentum will cause the wavelength to decrease. And this decrease in wavelength causes the theta to be smaller. So that means if you increase the accelerating voltage, your peak will be nearer and nearer to 0 degree. Okay, it will shift nearer and nearer to 0 degree if you speed up your electron to be faster by increasing the accelerating voltage. Okay, so this is how we relate between all the values, including kinetic energy, accelerating voltage, speed, momentum, wavelength, and theta, all in a single picture. How do you relate them together? Of course, our question is not that difficult, so don't worry too much about it. I'll provide a more concise summary in class soon. Okay, so before you move on, right, I'd like to point out something. If you study this particular chapter in your local reference book, you find that many of the reference book refer to this particular setup as the Davisson-Germer's experiment. Okay, they say this is Davisson-Germer's experiment, then they show this particular setup. And I believe you can see that the Davisson-Germer's experiment that we explained just now, there's no bulb in it. Okay, you don't see this kind of setup over here for your Davisson-Germer's experiment that we discussed just now. Okay, it's because actually I think this particular setup is not Davisson-Germer's setup actually. I don't know why many books tend to say that, many local books tend to say that this is the Davisson-Germer setup, but this is actually George Berger Thomson's setup to study electron diffraction. Okay, it's not correct, but it's not correct in a harmless way. Okay, because why? Because this particular setup also studied the same thing. It is also used to study electron diffraction, same as the setup that we have been discussing all this while. The Davisson-Germer setup and this George Berger Thomson setup, they are both studying the same thing. They are both studying electron diffraction. It's just that if you are referring specific to Davisson-Germer's experiment, it should be the setup that we have been discussing just now. This particular setup is actually George Berger Thomson's setup, but it's explaining the same thing. You can see that there's bright fringes, there's dark range, there's also bright fringes, there's dark region, there's bright, there's dark. So this is similar to the diffraction pattern that we have been mentioning all along. It's just that this one is more in the circular pattern. Okay, whereas for Davisson-Germer is more on the 0 to 90 degree kind of thing. Okay, but this one is more on the circular pattern that we can observe on the screen over here. Okay, but it's still the same bright and dark fringes, so it's still related to diffraction, so it is used to prove electron diffraction as well. Okay, in fact, right, if you want to look into the history of things, right, Davisson and Germer's figure out electron diffraction using their setup from just now, this particular setup. They figure out electron diffraction using this setup, right? George Berger Thomson also figured out electron diffraction by using a different setup, but they managed to discover it, or they managed to prove this de Broglie's hypothesis around the same time actually, and it's actually proven by someone called it's actually noticed by someone called Max Born. Okay, there's a long history to it, but they both independently do the experiment, means that they don't know each other, but they conduct a similar experiment to prove the same thing. Okay, so because they managed to prove the same thing, and this thing is so important, and therefore Davisson and Thomson without Germer, okay, Davisson and Germer is 2%. Davisson managed to get Nobel Prize, Thomson managed to get Nobel Prize, but not Germer. I'm not sure why. I didn't study into that detail why Germer didn't manage to get the prize. But that Nobel Prize in Physics is in 1937, and it was awarded jointly to Davisson and also Thomson for their experimental discovery of diffraction of electrons by crystal. So the idea is electron diffraction. That's the discovery that they managed to make, and it is a joint award, but they did the experiment independently without being aware of each other's presence actually. Okay. A fun fact is George Berger Thomson is actually J.J. Thomson's son. So J.J. Thomson actually discovered electrons also. Okay, so his father, George Berger Thomson's father, discovered electrons as a particle, but George J. Thomson refuted his father's statement, saying that it is not actually a particle, it can also behave as a wave. So it's sort of like a fun fact, like a father and son kind of disagreement, not really disagreement, just that his son managed to study electron more deeply and understand that it is not exactly just a particle, it also possesses wave properties as well. So some kind of fun fact of the Thomson family fun fact. Okay, so this sort of wrap up our discussion of De Broglie's hypothesis, how they relate between the various variables from accelerating voltage to kinetic energy to speed to momentum to wavelength and the angle for the Davisson-Germer's experiment. Then we talk about George J. Thomson also has his own setup, and they both wins the Nobel Prize together. Okay, in the next part, we are going to move on to other sections, and we are going to talk about electron microscope, which is a result of an extension of the study of Davisson and Thomson. We are able to create devices like electron microscope. So in the next section, we'll be talking about electron microscope and why is it superior compared to the light microscope that we have been using all this while.